It's my pleasure to welcome Draguna Vrabie. Okay, I just got the last name today. So Draguna is from Pacific Northwest National Lab, where she is a chief data scientist in the Data Sciences and Machine Intelligence Group. She was previously with an energy and power group there, and before that she was at UTRC. And she did her PhD at the University of Texas at Arlington. So she's going to tell us today about control design based on deep learning with some applications in power and energy systems.
Thank you. Thank you. Thank you. And thank you for being here. It's very exciting. This is the first time after COVID coming to a university and giving a in-person seminar. So my talk is called Control Design Based on Deep Learning. I think the two elements are control design and deep learning. And basically what I'm going to talk about is ways in which we have been introducing deep learning tools and methods in control design approaches. So my talk is going to be based on a basic understanding of model predictive control. So for those in the room or online who do not know what model predictive control is, I have this introductory slide, which basically tells us that model predictive control is a control methodology that makes use of models and optimization tools. And based on the model, one can make predictions and can optimize for the control decisions that would minimize or maximize a particular cost function. Then once the solution is found, the first decision is being implemented in the system. The system evolves over one sample time. Then measurements are taken again, and this loop is repeating. So this is an advanced approach to optimal control. It's multi-input, multi-output. It handles constraints very well, and it provides optimality guarantees. However, model-based predictive control, because of its nature of solving optimization in the loop, is computationally expensive. And that makes it unattractive to some areas of applications. And today I'm going to talk about this approach, which we call differentiable predictive control, which is a way to synthesize model-based predictive control solutions using deep learning tools and methods. So my talk is going to be all about this, how we started, what motivated us, what we can do for the system identification part, how we synthesize controllers, and how we start looking at stability and safety guarantees for these types of controllers. But the bottom line is we wanted a method that would take us from data to control policies. And the data is something you can measure from a system that you're interested in controlling. The first step in our approach is to do system identification. And to do system identification, we leverage deep learning methods. And in a form in which we're using both the physics knowledge about a particular system we're looking at, as well as the deep learning tools. And then once the system identification step is complete, we take the control synthesis problem as an offline optimization problem that utilizes this identified system model and trains a control policy representation that is a deep learning representation to maximize or optimize a particular loss function, which includes the traditional MPC objective and potentially other objectives. So my talk is going to be all about this, how we're making all the steps. Now, this slide is only here as a justification to show that these kind of approaches really work. There has been a recent publication in Nature sometime at the middle of the last year, where Sony showed that they can use reinforcement learning in a closed loop with a very complex driving competition environment. And they were able to train a controller that would compete with human drivers and be successful. And they did this by using reinforcement learning. So this is only showing that such controllers can be synthesized, even though the environments are very complex. So we're not looking at very simple systems. But what motivates my work is not necessarily video games. It's looking at the some of the applications, energy applications that are important for the Department of Energy. And one of these applications that is very motivational for this approach is building energy efficiency. So over the past 12, 15 years, I've been working in the area of building energy efficiency applications. And I've been doing so for these particular reasons. Buildings use about 40% of the US energy. This amounts to a tremendous amount of energy and it's a very large number when you think about cost of electricity. They use 74% of electricity and they contribute to the peak electricity demand. And when we say buildings, we mean two different types of buildings. Very large commercial buildings that are in the range of almost 6 million, very large square footage. So we are in one of such commercial building. This is an educational building. And 123 million residential buildings, okay? And these buildings have 50 to 80 years lifetime. And they are here to stay. The building stock is being replenished or new construction is being added to the building stock. So it's growing at 1 or 2% per year, but the existing building stock, all of these millions of buildings are here and will be here for a while. And this motivates our research to help better control these existing buildings to reduce the energy consumption. So when I say reduce, what is the actual potential that we're talking about when you think about supervisory control? It's actually a very large potential for savings. And if you look at MPC, it's 50% of the energy consumption in the HVAC system alone can be reduced by advanced methods, so by predictive control. This has been shown, it has been demonstrated in many different instances and in many different demo sites. And unfortunately, there is no solution that is easily deployable across the entire building stock. So we started looking at our data-driven approaches with the intent of making model-based predictive control accessible across the building stock, so that actually this 50% energy savings potential can actually be realized. Today, buildings are being controlled with a large set of rules that are handcrafted by engineers. So looking at MPC by itself, we know that there have been many successes, a lot of success of MPC deployment in aerospace and robotics, in very large industry. And however, when you think about buildings, there have been successes, but also there are many challenges with deployment. And there are two drivers of challenges. And one of them is the need for models, right? Model-based predictive control means you need to get a model of the system, and every single building in this commercial and residential building stock is different from another. And that means modeling is a very difficult component. And when you think about models, there are a lot of unknowns in buildings, and modeling is expensive. And data-driven models do not really generalize. So purely data-driven. The other component of the challenge comes from the real-time optimization that I mentioned before about MPC. And that means you have to solve these control policies online. And typical control hardware available in buildings cannot handle optimization solvers. So that is a cost component that has to be incurred by the building owner who wants to transition to such advanced control method. So we started looking at how to introduce learning-based approaches in model predictive control. And in this illustration, I'm basically showing the types of things that people have been successful at using machine learning approaches are typically in buildings are thermostats. These are typically available in residential buildings. They're also available everywhere in commercial buildings. But when we talk about controlling commercial buildings, we no longer talk about controlling thermostats. We talk about controlling these very complex heating, ventilation, and cooling systems that have multiple layers of complexity. There are many different types of equipment there that have their own internal control policies. And our goal is to co-optimize the operation of all of these systems simultaneously to maximize their efficiency and therefore reduce the cost of operation. So what do we do to add learning in MPC? Well, one thing people can say is, well, why not use reinforcement learning? And on this slide, I'm describing the challenges with reinforcement learning and the successes of reinforcement learning. So I think one of the main challenges is that reinforcement learning requires an environment for the agent to learn from through interaction. And in buildings, as I said before, modeling or creating a simulation, high fidelity simulation of every building is something that is intractable. It's very costly, it requires significant expertise, and it requires advanced tools that our engineers do not know how to use. So because of that, reinforcement learning is not the ideal choice for controlling buildings. So how can we introduce learning in model predictive control? So this is one perspective. This is a slide I stole from DOE program manager slide deck. The perspective emphasizes that if you purely transition MPC to a learning-based approach and you're trying to learn the model, you still need a lot of data to train these models. So one important aspect we need to take care of is leverage the data we have, but also leverage the knowledge we have about the system. So incorporating physics knowledge about the system with the data is important. And it's something we must do. Otherwise, we will never optimize buildings in the next 20 years. And the other things that can be tried, well, you can do a lot of things with embedding constraints in the structure of your neural networks. You can do transfer learning. There are numerous things we can try. And one thing, the things we've looked at were how to replace the optimization based approach with learning of a neural controller. So in order to guide you towards what we've been doing, I want to recap a little bit the different types of optimization methods that appear in control. So first, on the left-hand side, you have the online MPC. This is the traditional approach. It's an online optimization, and it basically solves for the decision that has to be applied at the next step. It doesn't really calculate a control policy. It just gives you the right decision at this time. It doesn't leverage past decisions when making future decisions. It just solves this problem over and over depending on the current conditions. A better approach that has been utilized in practice is explicit MPC. Explicit MPC is an approach that solves for a control policy, considering all the possible situations in which the controller might operate in. So it's a parametric optimization approach. However, the methods that have been devised for explicit MPC do not scale very well. So when you go to classes of problems where you have more control inputs and more states, this generation of the explicit control policy is intractable. So people have started looking at imitation learning in the form of using the MPC offline under a lot of different conditions, calculating all the different types of, or all the set of solutions that can be explored offline, and using this data set of inputs and solution outputs to train a control policy. So this control policy is trained offline from solutions that have been generated using actual optimization. And this is what we call imitation learning. So basically the neural network is approximating the data set that has been generated. And the last approach is reinforcement learning, which also can be represented as an optimization problem. It is offline from this perspective because it requires an environment to interact with. Typically, this is not really applied online. However, it has its own challenges because it's very black box. So it cannot really handle constraints like an MPC approach. So there are methods to bring more features in reinforcement learning, but those are very limited. So what we're looking at right now with this differentiable model predictive control is synthesizing explicit MPC solutions, but not using the traditional approach, but instead using neural networks. So in a way, kind of mixing these two approaches and getting approximate representations of the solution of the explicit MPC. And we do so by differentiable programming. So differentiable programming, it's an approach that uses deep learning methods to solve optimization problems, parametric optimization. So say you have a parametric optimization problem like this one, where you're looking for a solution map, which is basically your control policy, parameterized control policy by parameters theta, and you would like to find a solution that is good under all the possible scenarios defined by these epsilon I. You have constraints, you have objectives. So this is basically a traditional optimization problem that one can use also in MPC. What we do to translate it into a differentiable programming form is embed these constraints as soft constraints into the loss function, and then solve for this solution map by backpropagation and stochastic gradient descent. Okay, so what are the tools that we are using? So as I showed before, these are the typical classes of problems. So you have online optimization, parametric programming. So what I was alluding to is that we will take some of these tools from machine learning and incorporate them in this framework of parametric programming. And here is the approach to do so. So this is Neuromancer is a library that we've developed at PNNL that allows us to formulate optimization problems in a high-level language, like typical optimization problem from formulation tools, but solve these problems using deep learning. And the way we do it is synthesizing this computation graph, which basically starts with the data set and ends with the loss function. And everything in between are the control policy, the constraints that have to be satisfied, and of course they are in a soft form, and they all inform this loss function. And then through backpropagation, we propagate the errors and we train this policy. So this toolbox allows us to formulate problems at a high level, which is what we typically like to do, and solve them with deep learning techniques underneath. So underneath you have all PyTorch machinery. And of course, we're learning approximate representations of the control policy that minimizes this cost and satisfies these constraints. Okay, so those are the tools. Now, let me talk about the domain-aware machine learning. So you, if you look in the literature, you might be seeing this scientific machine learning and differentiable programming. Lots of people have started looking at modeling dynamic systems using deep learning methods. And this is a lot of recent literature. So everybody is working on this. They're looking at different types of systems. They're looking at different types of methods, different types of introducing physics knowledge into the neural network architectures. So we are obviously doing something similar because in order to do model-based predictive control, you need to model your system. So we've also developed a library that allows us to represent dynamic systems and train the parameters of these dynamic models, of these models of dynamic systems using, again, deep learning optimizers like stochastic gradient descent. So what our toolbox allows us is to formulate at high level what these dynamics look like, and then using again, parametric optimization to train the parameters. So we can go from this entire range between white box representation, which is typically a system where you know all the physics. Black box, let's say you don't know any of the physics, you just know that there is a state and that is evolving based on some unknown process. Or you can represent your system as being a gray box combination where you know some of the equations and you don't know some other ones. So in with our toolbox, you can represent all of these models, and then based on data, right, time series data of inputs and outputs, you can train the parameters, both the parameters that belong to the neural representation component of the model, and also the parameters that are unknown, like for example, in this case, this alpha parameter, let's say, is not known, but this is a fixed constant that everybody knows, as an example. So with the same tools of parametric optimization, we can solve this system ID approach. And we've looked also at systems that are more complex than that. So in this case, networked dynamic systems. Oftentimes you see these types of systems in engineering. Some systems they have physical interconnections, and let's say each node has a particular dynamic evolution. So we've looked at ways in which we can represent these and then train these models from data. And what we can do is not only recover qualitatively well the dynamics, but also we can recover the connectivity between the system. So for example, these adjacency variables. So again, this is an example of classic Ramote oscillators, and people are using it in power systems. Okay, so those are ways in which we can introduce physics. There is one more way in which we can introduce physical knowledge into the architectures of our models. And this is a way to enforce constraints in each layer of the neural model. So here we're showing how during training, at a particular layer, we can enforce that the eigenvalues are all in the unit circle. And throughout the training process, while these parameters of the layer are being learned, we can ensure that these eigenvalues of that particular layer stay within the unit circle. Okay, so it's a way of enforcing more constraints during the learning process, and you can do so with other types of regularizations. So, given these ways of introducing physics, we can train dynamic systems models from data. And this is very helpful for our approach. So this component here of representing the model and training it from data enables us to move forward to the predictive control synthesis. So that makes it our approach very applicable to a wide range of systems. Now, the relationship between MPC and differentiable predictive control I mentioned before. Here you're solving the problem over and over. Here you're learning the policy represented by these weights, right? This is online, this is offline. So all the computations are happening offline. So there is a lot of compute that has to be there to enable this, but it's an offline approach. And once we have the policy, we can simply transition it to a execution stage where you simply evaluate this policy without worrying too much about the compute time that is necessary. So you have an explicit solution. Now, how do we train these policies? So I showed you before for optimization a graph that shows how we introduce the constraints and the optimization objective. So for the control synthesis, it's a similar approach, right? So you have a data set. These are all the set points that you may want your system to track. And then you have these different representations, these different components here, like neural components, or they can be physics-informed neural components. So this is your data set. So all the desired trajectories that you would want your system to track, your control system. So now we're training controllers. This is the control policy that you want to train. This is the model of your system that supposedly we've trained it before using same type of approach from input-output data. And then you have constraints, min-max constraints on control inputs. You have min-max constraints on states and outputs. And then you have some elements of this loss function. Everything gets accumulated in this learning loss function. And then using backpropagation, we can differentiate through this computational graph for all the data, for every single point in the data set. And we trained a policy. We trained a policy in a way in which this loss function is as close as possible to zero, basically the error between what we want to accomplish and what we actually accomplished. So again, with our Neuromancer toolbox, formulating this graph, it's very easy. You only have to represent the optimization problem at high level. You do not have to bother yourself with like making all these connections and making sure that the information from here connects to information over there. So here's how it works for a very simple example, stabilize an unstable system. In this case, we assumed that we know the model of the system. So let's assume we did a system identification and this is the model. And we want to minimize this MPC loss function. So our DPC formulation basically amounts to training a control policy. So this is how the control policy is learning over time. It starts with, in this case, we're only showing the start from the same initial condition and it's the same objective, right? So over time, you can see how the closed loop control trajectories are changing while we're learning. Obviously, we're not only sending this trajectory sample through the training graph, but this is just illustrating how the policy landscape is changing while we're learning and how the outputs and the control input is changing. So here we had a constrained control input, and over time, it learns to stay within the bounds. This is a very simple example, right? It's just an illustration. Again, an illustration of the same thing and how you can introduce stochastic uncertainty. Again, instead of sampling only from set point trajectories, you add uncertainty and you sample from the set of uncertainties as well. So you get these kind of results. So again, a policy that optimizes this loss function, but taking into account the stochastic uncertainty. Another example where we looked at a simple double integrator that has to go from point A to point B while avoiding an obstacle. You can see that our differentiable predictive controller, once it has been trained, it can go between these 2 points, and then you can compare with the output from an actual optimization-based approach. And you see it's not always the same, right? Because DPC is an approximate approach. Okay, so we're able to train these control policies, right? So there is a theoretical connection with MPC. We have a lot of advantages. We can train this control policy offline. It is a parametric solution to the MPC problem. It handles state constraints, input constraints, and it's using differentiable models, right? The system identification part, right? And however, people will raise their hand and say, well, how do you enforce stability at the end? How do you guarantee that the state is not going to go out of bounds? And this is what I'm going to talk about next. So the approach is very promising, but there is more theory to be developed. Okay, so we started by looking at how do we guarantee stability. So here at the top, we're showing the representation that you've seen before. So you have the control policy, we're trying to learn the system model. And what we're introducing also is a neural representation of a Lyapunov function. And we train everything just like we did before. And we end up not only with a control policy, but also with a Lyapunov function that is showing us that the control policy makes this system stable in that particular region. And this is the same example I showed before, again, illustrative to input, to state example. Same type of result, but we also get this Lyapunov function. So how do we do it, right? Like we introduce not only these constraints, the traditional constraints, as soft constraints in the loss function of the deep learning control synthesis loop, but in addition, we introduce another constraint that enforces that this Lyapunov function that we will be learning, which is basically an input convex neural network, will also have to, this Lyapunov condition for this additional representation of the Lyapunov function is satisfied. So we take this and we introduce it here as another constraint in our learning process. And it works and it provides guarantees in the sense that as far as we sample enough, we get enough confidence that this Lyapunov function is telling us that the system is stable in that particular region. So this is another example for, again, a relatively simple system, a planar vertical takeoff and landing aircraft model. You see this in the literature. So we apply the same approach and we got similar good results for control, but also the guarantee that the system will stay stable. So from this perspective, we can say something about the stability of the system, okay? Things we are still working on is how to ensure safety, how to deal with time varying objectives, right? It's not easy, right? Like the loss function is fixed. It's not time varying. And in the types of applications that we're looking at, objectives can change. Okay. Now, how do we look at safety? And this is, I'm coming close to the end. So this would be the almost the last part of my presentation, is how do we deal with safety? There is nothing here that will ensure that the states will always stay within a particular area. So the way we started looking at this was by introducing this idea of control barrier functions. And we just started looking at this. We have a couple of we have one publication and a couple of others under development. So here, if you look at safety from this perspective, you actually want the state of your systems to stay inside a particular set. And you want to build these control barrier functions in a way in which when your state hits this boundary, it will be immediately pushed back inside. So how do we solve this online to ensure safety? Basically, you're adding this optimization problem to solve for a safe control input, and this has to be solved all the time as a safety assured verification step. I mean, not verification, assurance step. So this means you have to solve an optimization problem when the system is running. And that's not something we like very much. So the approach that my collaborators came up with was to look at assuring this step only when the state comes close to the edge of the set of the safe set, and for the rest to just apply the control policy that is coming from DPC. So basically, you have this DPC policy, and instead of solving this all the time, they were looking at ways in which to solve it less. So in addition to this, we looked at other things. So first of all, this condition is applicable for continuous time systems, and our approach for control is basically discrete time sampled approach. So the formulation of this condition had to be modified so that we can incorporate that during our training. Again, I said we wanted to reduce this online optimization, so we were looking at a range around this barrier set, so not to evaluate this all the time. And then we also wanted to look at time varying sets, because typically for MPC, those would be important. And on top of that, we wanted to make this predictive controller aware of the fact that there will be a control barrier function that will enforce these limits on its output. So we started modifying the approach, right? So we started looking at modifying our control barrier function, and that's how we added this set around this kind of range around the edge of the set. And that's where we would only solve for this optimization problem. For the rest, we would just simply apply our DPC controller. And we also modified the representation by adding this multi-staged time varying control barrier set that has to be enforced. And we modified the control barrier function constraint from a continuous time representation to a discrete time representation. And here we looked at this most extreme situation where you have when you actually reach your Lipschitz constant. So with all of these modifications, this is how the control policy looks like. So for most of this, inside of this set, this safe set, we're using the traditional DPC policy. And then when the state reaches close to the boundary, we apply this constraint. And as it's mentioned on the slide, if the DPC controller is trained properly, you never actually get close to this edge. But if it's not, you might get close to that edge. So how do we train this? We introduce this constraint again in the loss function of the DPC training. And basically we formulated this constraint, taking all the steps that I mentioned before. And then we trained the control policy with this extra soft constraint. An alternative method of doing that is to actually introduce another constraint at the output of your DPC controller. So you have this projection-based approach that helps propagate only the control inputs that keep the state of the system within the constraints. So either way, we're training DPC control policy. So we took this example to show like how does it work, right? So how does it compare where you only have control barrier functions, where you have DPC only, or where you train it properly or poorly? And this is the example system that we looked at. It's, again, a relatively simple example because we're just starting to look at these methods. So the red line is the set point that we want the output to track. The black lines are the constraints that define the control barrier, the control barrier. So you don't want the output of your system, or the state of your system in this case is the same, to get outside. And this is the control barrier function. So if you train, if you do control barrier function only, you make sure that the state of the system stays within, but this is the kind of results that you can get. It's not really tracking this set point very well. If you do DPC only and you don't consider the control barrier approach, DPC, if it's poorly trained, it might come out of that set. And if DPC is poorly trained, but you incorporate the control barrier function approach to the training, you end up with good trajectories that when they step outside, they get pulled back inside the safe set. And ideally, if you train the DPC in a way in which it becomes aware of the fact that there is a control barrier function that will pull it back, you actually get the best performance, you get the best tracking, and the output never comes close to the edges. So the control barrier function actually never gets triggered. Like you don't really trigger that aspect of the policy because you inform the DPC controller that it shouldn't go there. So this is the summary. These are first steps we took to add some constraint satisfaction, hard safety guarantees into our DPC approach. And next steps, obviously, this was a very simple system example, and we want to look at more general system representations, and we want to look at ways in which we can introduce adaptive learning in this process. So right now, all of this is offline. Now that we are convinced that there is a way to ensure constraint satisfaction and safety guarantees, then we can start looking at ways in which we can learn online from real-time measured data. So this would be our next steps, right? We automate the learning process for the system model and the control policy. We want to look at adaptive approaches where these systems can learn from real-time measured data. And we're also interested in integrating this type of control approach in these larger frameworks of control co-design, where not only you can synthesize the controller, but also can inform on the parameters of the system that you are trying to control, and basically simultaneously design your system and your controller. So I'll end here. These are my collaborators. I would like to acknowledge Jan Draguna, Aaron Tour, Wenches Shaw Cortez, Sayak Mukherjee. So they and our sponsor funding agencies and internally funded programs at PNNL that supported partially this work. And I will take questions. Thank you. I know it's a lot. It was a lot. And maybe too much.
Yes. Question, and when you were explaining the training of your network differential equations, so are they like suites like this, or is it added?
They're added.
They're
added. Yes.
And what are we training? Is it parameters in the differential equations or parameters in the addition in that output?
When we look at the system identification, we're training the parameters in the equations.
The output. In the differential equation?
Yeah.
Okay.
For the system ID. And that includes also the parameters of any kind of neural model that we include in the system ID. So yes, and then when we're training for the control policy, we're only training the parameters of the control policy.
It's just a question.
No, you can go ahead. You can go ahead.
I was going to ask about the control barrier functions, and you started with this kind of perspective of MPC, and there's a horizon, and you can look ahead, as opposed to the control barrier function, which is making like an instantaneous decision.
Yeah.
And so, could you just talk a little bit about like those two different perspectives and like doing control barrier functions maybe with the horizon ahead?
Yeah. So that's what we were trying to do here, and we were basically trying to represent these conditions on a horizon, and knowing that the control barrier function, if the set point is changing, right? So at the end of the day, the definition of the set points that the system needs to track, they are part of our sample set at the beginning, right? So once we define those, we can also define the safe sets around those. So all of this is known at the beginning before we train so it's basically some bookkeeping of all of these things, like what happens over the horizon, and keeping track of that when we compute the loss function that we need to evaluate at the end. Yeah, so far. I mean, I'm sure there are more ways in which we can look at this, and I think this is pretty open research area. It's just the first thing that, well, Wences Shaw-Cortez, who led this work. He's an expert in barrier function control based on barrier functions, so safe control. And that was his way of approaching this mix between DPC and barrier functions.
I have a question on that. So for this, in this slide, if X is outside of AT, we just take the DPC policy. If it is it belongs AT, we solve this QP problem. But if there is any difference, if it is outside AT, we just also solve this QP problem, but it just give us the same solution, because we just minimize this. So this is the same, right?
Yes, yes.
Okay, thanks.
I have a more practical question. So doing these, did you get any insights as to what type of loss functions are easier to train, or like what type of policy structures are easy? Because whenever I have a student try to train something, they will come back and complain that, oh, this is not converging.
Yes.
It's like,
Yes.
are these well-behaved problems, or can you get any insights as to like, how should I treat my parameters to get something?
They're not very well behaved, I would say. So there is a component in this entire work that I didn't really talk about, which is the computer science aspect of it. It's like, how do you train? How do you sample? What do you do during training? So we are using a lot of tricks from the computer science bag of tricks to train these models and to make sure that they are behaving well. And it doesn't, I would say it's domain specific. The approaches we take are domain specific. So currently we are looking at approaches that would work for systems like building energy efficiency, like building systems, HVAC. But I think it's going to be domain specific. So depending on what we're trying to control, we might have different rule of thumb for how to apply these deep learning methods to make sure that you train in a reasonable amount of time with a reasonable amount of data and so on. So one thing we notice is that it's not a good idea to start with the long prediction horizon for the MPC from the beginning. So we start with training the models for shorter prediction horizon. And then once you get some convergence there, you increase the prediction horizon and continue training and so on and so forth. So tricks like this, sampling, how to sample, what kind of set points to sample. It's a lot of computer science methods that we use. Yeah. Yes.
May I ask, when we embed this kind of real-life functions in the agents, how can we prevent it from building this experience of some risk actions? Because typically we use some optimization by inner approximation to estimate the whole region of projection. But in reinforcement learning, maybe you will take some risk action. So the agent will contain some experiments about the risk action there. So how can we call it a reliable? I mean, how can we call it a sense of, they have a sense of stability?
Yeah, I think that's the challenge with reinforcement learning, that it's difficult to ensure. So it relies on being able to explore outside of its comfort zone. And during the training with reinforcement learning, you actually want to get these failure situations, while here we don't want to have that. So I think, I don't know. Did I answer your question in some way?
Yeah, thank you.
Okay.
You mentioned that with this approach, you learn a control policy and also the Lyapunov function.
Yeah.
Can you explain a little bit more how was the Lyapunov function learned?
In the same way, so basically, if you look at this picture here, the Lyapunov function is a neural network representation. So it's not what you see in the picture, right? It's another neural representation that we learn. And this neural representation of the Lyapunov function gets the states from the system model, and it provides its evaluation to this loss function. So let me see if we have a complete here. Actually here. So we added this element in the loss function. So we trained the parameters of the neural representation of the Lyapunov function to ensure that this constraint is satisfied. So basically we added more soft constraints in the loss. Yeah.
One follow-up on this is the outcome function, the condition is verified for all the possible state or only the training data you get?
Well, yeah, basically only for the training data, right? So it's only providing the guarantee in the statistical sense that, you know, if you sampled enough and if you sampled in the regions where you actually want to get the result, then this is providing a stability guarantee. Otherwise, yeah, it's not. It depends on the sampled, on the sample data.
In the application setting, this kind of statistical guarantee is satisfied for the user, or?
So I think it depends on the application. I think for this type of systems where the risk is not high, if it goes unstable for a little bit, it's okay. But yeah, generally people don't really prove this kind of property of the system if they use neural networks. I guess this could be used also for like reinforcement learning controllers. Like once you train a controller, you know, can you synthesize such a Lyapunov function that gives you some kind of guarantee, at least in a statistical sense, that the controller is providing you with stability. Yeah, so yeah, it depends on the data, of course. Yes.
Have you had success training or using these controllers to actually control commercial buildings or HVAC?
Simulation models so far, yes. Currently, we are working with 4 industry partners who deploy control systems in actual buildings. And we are looking at ways in which we can take our methods and incorporate them in their own control frameworks. And yeah, so far we believe this will work based on all of our simulation-based results. Yeah, but it's going to be fun for the next 2 years to work with these industry partners and see what we can do in the real world. Yeah. Yes. One more.
Yeah, just a quick question. To follow up on that question, in terms of one of the big successes of reinforcement learning at the enterprise level, as for example, Google using reinforcement learning to optimize cooling for their server centers. And I think they are Google, so they can do anything they want. So they can model and build environments of this particular building and optimize for it.
Yeah.
And your motivation for this work is building something as a framework which is kind of building agnostic, so you can apply it everywhere. Could you point out in your DPC framework which part is allowing your policy to be transferable to these different contexts?
Which part? I would say this. So if you look back, let's just look here on this picture. So I would say that if we have 2 systems that are sufficiently similar to each other so that their models have similar structure, but maybe just different parameters, then the control policy trained with one model, potentially we can look at some conditions under which it would be transferable to the other system. So I would say it all starts from the system model. So if you have some kind of degree of similarity between 2 systems and you have a good model trained for one of them and the other one, let's say the parameters are not that far away, then we can start thinking of like under which conditions we can transfer the policy. Yeah. Does that make sense?
Let's thank Draguna.
Thank you. Good. Was it easy to understand and follow?
I mean, like, not, I don't. Yeah. Or not.
All right.